So in last lecture, we learned about the momentum fluxes, and one thing that we should note is that the transfer of momentum flux would always take place from the point of higher potential to point of lower potential. And hence when we are talking about transfer of momentum flux, we know that the velocity profile matters or varies in the direction, that is that as we move away from the boundary layer, the velocity of wind or u component of velocity will keep on increasing, and hence momentum flux would generally take place from the upper layer to downward layer. And to reflect that, tau is sometimes written as negative of rho nu del u by del z, and this negative sign is the correction for the direction, that to highlight that this flow should always take from the point of higher to lower potential. Also, when we talked about these processes, we said that we will discuss the radiation in next lecture, because radiation is a central concept in hydrology, because this is one of the prime form in which we receive energy from the sun. Now, radiation, as we discussed, can also travel through vacuum, and hence if we have sun and the energy is emitted in packet of light, what we also call as photons. And the reason these called as photons, because the dominant portion of spectrum is occupied by the visible light. Now, when this radiation strike the earth, this can either be absorbed or it can be reflected back, and this absorption and reflection happens at multiple layer. So one layer is the extraterrestrial layer, what we also call as the layer or the boundary of atmosphere. Now, once a particular photon is able to penetrate into atmosphere, it can also get scattered because of presence of various aerosols, gases that are suspended in the atmosphere, and finally if it is able to reach the earth, it will be absorbed. So part of it would be absorbed and part of it would be reflected back. So whatever the earth absorbs, it primarily goes into two areas. One is to change the temperature, and we call that whatever portion of these radiations result in change on a temperature, that is typically referred to as sensible heat. Also, some portion of it will go to change the phase. So snow will change into water, water will change into vapors, and that may not be associated with any changes in temperature, because we have learned that whenever a phase change is happening, we absorb a lot of energy and temperature may or may not change. And that's what we talk about latent heat of vaporization or latent heat of sublimation, where the material is or matter is changing state from solid to liquid or liquid to gas without any significant change in temperature. Now, what we are concerned in hydrology is the term called as albedo. And whenever you will read any hydrological model, they will frequently mention this word albedo. So albedo is referred to as the fraction of light that is reflected back. So if we talk about water, so water has very low albedo of around 0.1, which means that it will absorb 90% of the incident radiations on its surface. That would mean that the albedo is low, because albedo represents how much is getting reflected back, and only 10% is going to get reflected back. Similarly, if we talk about snow, snow has albedo as high as 90%, which would mean that it would only absorb 10% of incident radiations falling on it. Now, when we talk about measurement of evaporation or evapotranspiration, we would be interested in how much energy we are receiving, and we would be talking about net energy that a surface is receiving. So we can look into the expression of Rn as Ri, that what is incident, minus alpha times Ri, what is reflected back, and minus Re. So when Earth receives energy from sun, it is typically received in form of short waves. And when Earth emits, as Earth would have certain temperature, and we know that from basic thermodynamics that any body which is above absolute temperature, it would always radiate energy, and that radiation always takes place in the form of long waves. And these magnitude of these long waves is controlled by the Stephen-Boltzmann law, which says that rate of emission by a black body is given by sigma times T to the power 4, where sigma is Stephen's Boltzmann constant, which has a value of 5.67 into 10 to the power minus 8 watt per meter square K raised to power 4. And whenever we talk about energy budget in the context of earth and atmospheric processes, this watt per meter square is the unit that we frequently encounter. And when we will talk about certain climate change notations, we will often express future climate change pathways in terms of representative concentration pathways, which represent net change in radiative forcing, which are also expressed in watt per meter square. So namely, we deal with RCP 2.6, RCP 4.5, RCP 8.5, which represent that how much radiative forcing has changed. And when we talk about RCP 2.6, we are saying that the radiative forcing has changed by a magnitude of 2.6 watt per meter square, or we have added that additional forcing that results in additional heat added to the atmospheric system. Also, since none of the bodies that we deal with, they are perfectly black bodies, so we include a factor called as emissivity to correct for RE. And this RE helps us calculate that what would be the net radiation that would be emitted by the Earth's surface. Also, when we talk about the emissions in form of radiations, we are essentially dealing with waves. So the two characteristics that are important to understand are the wavelength and the frequency. Now, how we would determine the wavelength of emitted radiation? So this radiation's wavelength is governed by a law called as a Wien's displacement law. And Wien's displacement law states that the wavelength of emitted radiation is inversely proportional to temperature, and this is given by introducing a constant whose value is 2.90 into 10 to the power minus 3 upon T, where T is in Kelvin, and this is the constant, of course, and lambda is in meters. So with this, we can determine that if a particular body is at certain temperature, so if we tell you the temperature of Earth, you should be able to calculate what is the wavelength of radiation that would be emitted. Also, we learned that albedo measures the proportion of incoming radiation that is reflected. Moreover, when these radiations enter into Earth's surface, they will encounter certain aerosols, certain particles, and that would result in the scattering. And if we have more and more aerosols, that may trap the outgoing radiations and send it back towards the Earth's surface. And this effect, where these added aerosols result in increased backscattering, is called as greenhouse gas effect. And this is said to be prime forcing that has intensified or accelerated climate change in recent times. And we will talk about this climate change, that what it means in the context of precipitation, evaporation, and impacting critical infrastructure systems as we go forward. Now that we understand that what would happen to a radiation entering into Earth's surface, we can always write the energy budget, and we say that net radiations are equal to the sum of solar radiation received on Earth per unit area, which we represent by RS, and atmosphere will also act as a radiator. As we said, more greenhouse gases would result in backscattering, and these aerosols would also be at a temperature which is greater than absolute zero. So they will also emit long wave radiation that can reach Earth's surface, and part of it would again be rejected given depending upon the albedo of a surface. And then of course Earth will reflect back or emit, not reflect back, will emit certain radiations as it is a body above absolute zero temperature. And when we look into the energy budget, so what happens is that if we have 100 units of incoming solar radiation at top of the atmosphere, around 51% of it reaches the Earth's surface, and out of these 51 units, 21% or 21% of total, it is emitted back as long wave radiations.
So only 51 reaches, 21 is reflected back as long wave radiation, and hence we are left with net 30 units of radiation on Earth's surface. Out of this 30 units, 23 units are used to power evaporation. We know that cloud formation is a result of evaporation and many other processes, but the key driver is the sun's radiation, and we see that large portion of what we receive is used as to change the phase of water, and only 7 units are used to increase the temperature of Earth's surface, which we also call as the sensible heat. And all these processes, unless perturbed by addition of greenhouse gases, they are in perfect equilibrium and they keep on going. And as we add more and more fossil fuels or aerosols, we perturb the system, and then system tries to reach a new equilibrium, resulting in increase in temperature, and that's what we say is the prime driver of climate change. Needless to say, radiations, energy balance, or vertical transport as well as horizontal transport are going to be the key mechanisms that we will use time and again to understand the phenomena of precipitation, evaporation, and that is the prime target of the subject of hydrology. In the next video, we will try to understand some basic properties associated with water vapors before we start looking into large scale drivers of precipitation. Thank you.